All right, let's get started.
I think they are identical.
All right, so a lecture about nothing. I gave this lecture a year ago, and then I made some additions to it over the last 2 or 3 days that bring some math in, so that's why I'm disappointed Mr. Lair's not here. But you'll see what I mean about a lecture about nothing. Hello?
Oh, now the arrow key should work. Present is now.
Where's the...
It's the present button.
Left.
Right there.
Oh, I see what the problem is. The mouse...
It wasn't actually centered on that window. You're right clicking. Yeah.
Okay.
The arrow key should work now.
Or hopefully the space bar. Okay, we're going to talk about nothing. So, did anybody see this a year ago? Remember it? It's a little different now. So, every time I do it, it'll get a little better, I hope. So we have a completely empty box. Yeah. And there it is. It's a blue box, but it's completely empty. And we have used something called a vacuum pump to pump out all the atoms, which is very hard to do. I mean, even in deep space, there's an atom or a molecule every few centimeters, and even in the deep. But let's imagine, it's a thought experiment, that we have a vacuum pump. I could have drawn that on here, and we suck all the air out. And also, the box is made of a material that doesn't do something called outgas. Outgas means if you take this tabletop and make a box out of it and try to evacuate it, material will come out of the plastic surface continually. All materials kind of evaporate a little bit if you have a really strong vacuum. But this is a magic box, and it's perfect, and it's completely empty. So what's in the box? Well, there are no atoms, but there is something else. There's black body radiation. We're going to talk about what that is. So the box may be empty of material, but it can have light in there. And light is what is made of what? It's energy. So right away we get into an issue. Light is made of energy. And then there's this. So there is something in the box. Even when it's empty of all the particles that we can detect, there's energy in the box. We'll talk about why. And it's equivalent to mass. So what is this strange black body radiation? Those of you who are taking physics now will see something about this in the spring semester, am I right? Okay, so let's talk about it now. You'll see it in more detail in Mr. Hanklin's class. And it's related to two things. It's related to something I showed you last week. This is Planck's radiation law for black bodies. It has this very interesting structure. Let's review the units. Planck's constant, the speed of light, the wavelength of the light, Boltzmann's constant, which pops up all the time when you're doing thermal physics, and temperature. So if you mix all this stuff together, you get curves that look like this. I showed something like this last week. It has peak. This is color. Here you can see human wavelength sensitivity is here. Ultraviolet over here, infrared over there. And it's not symmetric. You see what I mean by symmetric? The curve does not look like that, where it has the same amount on both sides of the peak. So this is a unique curve that Max Planck invented 120 years ago, and it explained something that was a mystery for the 25 years prior to that, and it introduced what we now know about quantum mechanics. And the Stefan Boltzmann law is very interesting. It says if I integrate this, so if you haven't had calculus, you wouldn't know how to integrate it. It's kind of tricky anyway, even for experienced calculus people, but if you integrate it, you get a surprisingly simple result, that the energy, the total energy in the box is equal to this constant, it's a physical constant, times the temperature to the 4th power and the area of the box. A bigger box will have more energy and a smaller box will have less. This is the surface area of the box. So if it's a cube, this is 6 times the area of the solid. Everybody's familiar with that,
Don't
right?
believe it.
Not done with magic. So the interesting result is that, and this is true of all objects, this empty jar, nearly empty jar, if you look at it in the infrared, it's radiating a total amount of energy that depends on its temperature, its surface area, and this physical constant. And the amount of energy goes as T to the 4th, which is kind of, don't often see that in science. We see R squared. Things to the 4th power are not that common. So now we know the interior of the box, no matter how cold we make it, remember there's a T here, temperature. We can make it extremely cold, but you know there's a limit to how cold you can make something. Absolute 0. Takes an infinite amount of energy to drive the temperature of something down to absolute 0. And now I'm going to make a little diversion here and say something Mr. Hanklin maybe knows. I was at a cross-country race the other day, and I bumped into my friend Carl and Lisa Pendergast. And Lisa works at a thing called Cold Quanta. It's a small company in Boulder, and they make a machine for making extremely low temperatures. Not absolute 0, but pretty close. And I asked her if they have an outreach person who might be willing to come over here and talk. We'd have to assemble a bigger audience. And she said, yes, they do. And so they would have somebody come over and maybe bring a model of their machine. It's a machine about the size of 2 of these tables put together. And if you run it for a couple hours, it'll make Bose-Einstein condensed material. And it's not that expensive. If somebody had some money to donate to this school, they could buy one. It's like $150,000.
That's not that bad, actually.
Yeah, for scientific experiments these days. Okay, so I'm going to keep poking Lisa and Carl and see if Lisa will come over and bring someone who can talk about Bose-Einstein condensed matter.
That'd be great. And
this will be a factor. How cold can you make the box? Okay. We already did this. All right, so the way this unfolds, the equations have to appear first. I just showed you this. The total energy in the box is equal to sigma, physical constant, related to the Boltzmann constant. It's called the Stefan Boltzmann constant. That's not important. T to the 4th. We'll talk about the other one in a second. Okay, so we can control the amount of radiation in the box by changing the temperature. Here it is. It goes as T to the 4th. A human body is radiating all the time. And one interesting question is, where is the peak of the curve? Remember, this curve has a peak. And prior to Max Planck, people had measured where the peak is, and they learned this law, that the peak of the curve, lambda max, times the temperature is equal to about 3,000 microns, that's measuring the wavelength in microns, times kelvins, measuring the temperature in kelvin. So we go over here, and this is called the Wien or Wien, depending on if you're from Germany, displacement law. So this has an interesting property that everybody should memorize. Lambda max times T equals 3,000 if the units are in microns and kelvins. So if I say to you, the temperature of the sun is 6,000 Kelvin. We'll put 6,000 here. What is the wavelength of the peak of sunlight outside our atmosphere? Well, we already had this. I wrote this down just right there. What's the answer?
555 nanometers.
3,000 over 6,000 is a half, right? So, and if you go out in outer space and measure the black body curve of the sun, you get 0.5 microns. This is a pretty reliable way to, how about a human body? What's the temperature of a human body in Kelvin? What?
28 C.
In kelvins.
Well, yeah.
It needs to be the external temperature.
External temperature, let's call it 300, right? 273 is 0 centigrade, and add, would you say 28?
Yeah.
Very close to 300. So what's the wavelength of a human peak of the wavelength of the black body curve of the human body? Spit it out. 10 microns. And if you go look at if you purchase or borrow or rent an infrared camera, you will find the peak of the black body curve is at 10 microns. And black body has another interesting property that I want to remind you of. So here we have wavelength and the energy at each wavelength. And let's say this is the sun, that's 6,000 Kelvin. If you now go and have go look at and measure a fireplace in your home, it's not 6,000 Kelvin, it's more like 1,000 Kelvin. The curve has the same shape, the peak moves, but these curves never cross. This curve and this curve never cross. Suppose you look at a human body, 300 Kelvin, it will have something like that. And the Wien displacement law depicts how the peak moves as a function of temperature, right? There's the temperature. So if this is 300 Kelvin, 1,000 Kelvin, and so forth. So this dotted line is the Wien displacement curve, which you should all burn into your brain. The black body curves never cross. Now there's a little more complication to it because not all surfaces are good emitters. For example, this black plastic they use on the tabletops is a really good emitter. So the energy comes out with, that's measured by something, epsilon, which stands for emissivity. So for something super black, the emissivity is very close to 1. For a shiny metal surface, the emissivity is very close to 0. It can be warm, but if you put your hand near it, you don't feel any heat radiating from it, because if it's a polished surface, it doesn't want to allow that radiation to leave. Okay, so now we're going to do what I said we were going to do a few minutes ago. I'll edit this part out. We're going to stop and then restart the recording.